Okay, so let's start our physics online colloquium. This is actually the first one this semester, and we are very happy to have Professor Sudeshna Sinha from either Mohali, and she will talk about harnessing chaos. So I will hand it to
Okay.
uh, Professor
Okay.
Sinha to begin the talk.
Okay.
Actually.
Okay. Okay. Thank you, Arpun. So what I thought I would do today is to share one particular thread in my research interests. And this thread involves efforts to use our understanding of chaos for a very specific application. It's an application which we all know and love, ubiquitous, namely trying to design slightly different computing devices. Okay, and I thought I'd choose this particular research thread over my usual more theoretical musings, just because, uh, eh, just perhaps to show that sometimes completely abstract constructs and ideas do find a way into applications. And when it does, it's great fun, and it's more fun for theoreticians like me, because essentially applications don't quite figure on our mental landscape. So but when it actually, maybe by accident, while you're chasing your own ideas, if you do manage to stumble across some applications, it seriously is a lot of unexpected fun. Okay, so that would be what I would try to convey to you today. So see, I don't see how to, one second, when I okay, I think that wasn't the best way. It did change the slide,
Yes,
right?
yes, yes.
Okay,
Unfortunately,
okay.
that has to be like that actually.
No, 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 that's okay. Okay. There's always something. Okay. So what I thought, since I don't expect an audience of specialists, I thought I would start with a very shallow, very brief introduction to the concept of chaos. And I mean, this is one of the two words in the title. It's the briefest title, two words. So at least one of them I should explain a little bit. The thing here is that in some sense, we are dealing with classical phenomena. I mean, and when you say classical, it's perhaps a polite way to say really old. Okay, so in some sense, you would have thought it's a done and dusted, a field. But what always strikes me, to put a spin on Wigner's very famous quote, is the unreasonable effectiveness of classical mechanics. It really gives us this mathematically rigorous toolkit, which seems to be so useful to understand things over scales which are mind-boggling. From nanomechanical oscillators, my friends who have a lab here are forever looking at duffing, for instance, or astrophysical objects, which is like right at the other end of the scale. So it almost has no business being this good. Okay. Uh, and you can think of, but still there have been niggling feelings that there are aspects of the classical system which are not quite fitting with this whole idea of a clockwork universe, which comes out of really neat, clean mathematics. So these are the ideas which pushed forth and needed a new concept, and which is the concept of chaos. So you can think of it as a new frontier of classical mechanics, slightly grandiosely put, or sort of like a new kid in a very old block. Okay, and in some sense, it actually has, even if calling it a new science might be a stretch, it still has caused a very fundamental way in which to assess a classical physical world. Okay, so this is what I will just go over a little bit. Okay. So clearly, something has to necessitate it. You don't push yourself unless you need it. And what was the surprise? So the surprise was that seemingly very simple natural processes seem to exhibit extremely complex behavior, which defied, the simple elementary functions which we know and love to describe dynamics. And it was so complicated that it often appeared as if they were evolving under random forces rather than a deterministic system. And so basically very completely deterministic system, no stochastic influences, displayed exponential sensitivity to initial conditions. And this actually made it, in effect, unpredictable. Very bad news for astrologers, but I mean, this is what was observed over and over again with simple systems. Okay. So this really necessitated a paradigm shift in understanding classical systems, and led to a whole lot of fairly rigorous study, which could be called a new science of chaos theory. Okay. Uh, what I find somewhat interesting here is that there is a little bit of sociology here too, because chaos has enormous common usage, especially in India. I mean, you use it to describe traffic, politics, what have you, joint families, everything is chaos. So it's a very, very overused word, in fact. But at some point, a word which was so commonly used made its way into technical literature, and in recent times, in some sense. So I just thought I'll put up one slide. I had a Greek student once who said that it was also there in Greek cosmology, apparently, something to do with uh, you know, the emptiness which comes before order. So it's like a pre-order. Okay, so it's not order. It's not so it's sort of a juxtaposition of what you would think would come before things organize themselves. And my Chinese friends tell me that there's definitely a Chinese symbol for chaos, which is this one. Let me just see. Even I can't quite see my own slides too well. Can I just take one? Okay.
Yes.
Okay. I'll just let it be. Huh? Okay. Okay. Huh. I'll live with it. Huh? Okay. You all can see it, right? Even if I
Yes.
can't. Huh?
Yeah.
Okay. 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 So I'll continue. Yeah. So as I was saying that my Chinese friends tell me that there is a symbol for chaos, and I kind of ask them, is it sort of the Greek meaning? And apparently it is the same sort of pre-order, or the extremely disorderly state before order comes in. And so in that sense, it's not too different from the Greek meaning. Uh, but now, of course, we have our Webster dictionary meaning of chaos, and it would say things like confused, disorderly, unorganized, you know, something which seemingly is quite random. So this word was sort of inducted into the technical literature somewhere actually around maybe the early 70s. In fact, I think perhaps this paper by Lee and York in American Mathematical Monthly is the first paper, probably, where the word chaos appears as a technical term in the title. The paper was Period 3 Implies Chaos, and it was actually a theorem by Lee and York. And I don't think it's probably before this paper, it hadn't quite, even though people had described phenomena, which we know fits the theory, I don't think the word was quite used before this time. So after this time, there was an explosion, and lots of people used this word to exactly describe a certain set of phenomena. So what are they exactly talking about? So I borrowed Ian Stewart's very popular book title, Does God Play Dice? And this is the key idea. The present determines the future. It's a deterministic system by definition, okay? But the approximate present does not approximately determine the future. And so basically, there is irregular motion from deterministic dynamical systems, which was very sensitive to initial conditions, so much so that it was impossible to predict it in the long term with anything less than infinite precision of the representative analog value. So this actually makes I have put it in this way here because a whole lot of us like to do numerical simulations. We take differential equations which are intractable analytically, and we put it in, on our computers, and we numerically integrate it. And here, this last bit is extremely important, because if we work with finite precision, which we pretty much always do, and then it tells you that essentially what we get is not going to have predictive value beyond a point. And the interesting thing is that people had felt uneasy about this for a long time, and people had flagged it in different ways. Okay, not in this language which I have put it here, but even Maxwell had felt uneasy about it. Hadamard Poincaré, of course, because he was trying to do the three-body problem, because everybody does the two-body problem. It's a textbook problem. Our students need to do it in their exams. But you come to the three-body problem and all bets are off, and even Poincaré is flummoxed. People were beginning to recognize that the whole idea of the classical world being like a clockwork universe was beginning to crumble. And Lorentz was perhaps, this is Edward Lorentz of the atmospheric group in MIT. He was one of the first people who actually observed this problem of imprecision in computer simulations having an enormous effect. Okay, so it was probably by accident. He did what a lot of us do when we do simulations. You go for a long time, then you save the last value, go for lunch, you come back and you say, I'll start from there and do the rest of the trajectory. And so you keep as many bits as you think is respectable. But what he found was that it was extremely sensitive to the number of bits he preserved in his calculations. So of course, now the concept is very popular, and as a sign of its popularity, it has bestseller books, all slightly overstated, but doesn't matter. Sold many copies, even had Hollywood movies. I mean, that's like, the ultimate, whatever, penetration of an idea into the psyche, I suppose. Okay, so it's one of those things. Like the butterfly effect is literally, thrown around without quite, precisely meaning this, but it's very popular. Now, let me just, my last couple of slides on this. So my apologies to all the experts in this virtual audience. Please bear with me for a few more minutes. I thought I should, at least start off a bit easy. So let me put a slightly imprecise characterization of chaos. So it is sustained, disorderly looking, aperiodic, long-term evolution. You do a Fourier transform, no peaks, looks like grass. So, and this keeps going. So it is not like it's a transient part of the phenomena and then it settles into a cycle. Not like that. It's a sustained behavior. And owing to great sensitivity, which, as I said, it appears almost random, as unpredictable as it can possibly get. So the precise signature of chaos picks up from this last bit. So if I had to have one, quantitative signature of chaos, I would say it is the positive Lyapunov exponent, which is precisely given as this, where these are the infinitesimal differences between nearby trajectories. So it captures the rate of growth or the rate of exponential divergence of nearby trajectories. But do realize that this particular definition is pretty hard to actually calculate because it involves two limits, both of which are very delicate. One is, that these trajectories have to be infinitesimally close, and the other one is, of course, t going to infinity. And for people who do this in numerics know that it is these two limits are quite difficult actually to reach with confidence. But it is the gold standard of of quantitative measure of chaos. Okay, so I just had two little examples because I've been saying this right from the start. Simple systems are giving you complicated behavior. And the reason I keep saying it is because if a very complicated system gave you very complicated behavior. I mean, like, what's the surprise in that, right? I mean, you throw in all kinds of things into something and something comes out, you're not that impressed. But the point here is that an exceedingly simple system can give extremely complicated behavior. So I thought I'd show you just two examples. So one of these is the simplest example you can think of, which can exhibit chaos, which is a non-invertible one-dimensional map. So a map is a discrete time dynamical system. It takes your state at time n, and through a function gives your state at time n plus 1, and where n is an integer, so it's a stroboscopic sort of following of the system. And the only common thread is that it's non-linear, all these systems. And notice it's 1D map, right? It is technically non-invertible, that is to say its pre-image is not unique, and that is actually necessary to keep things bounded. Now, three examples here. One is the logistic map. It has the simplest non-linearity, quadratic. So it has an x square out here, okay? First possible non-linear term you can throw in. These two actually are piecewise linear, okay? So they're non-linear, but they're piecewise linear. The tent map actually looks like a tent, two pieces like that on an interval 0 to 1. All of these are defined in the interval 0 to 1 to keep it bounded. And this one is a binary shift map. It's one of the nicest maps because it actually is a shift register. And this one is just 2x, mod 1 is what puts it back into the interval. So it's like two straight lines like that. And essentially, I would say there are two actions of these map. One stretches it, which gives you the positively Lyapunov exponent, and there is a fold operation. That is the non-invertibility, and that actually pulls back the iterates into the interval to keep it bounded. You see, if two trajectories run away infinitely to infinity, exponentially fast from each other, again, it's not so exciting, right? Both of them are running away. But suppose this whole thing is constrained to come back into that same region. So then imagine the complexity that locally they are flying apart, but they have to get back to the same space where they are kept bounded. So that this fold operation also is very important, not just the stretch. And here is something you can get by just doing a 10-second run of this iterated equation. So this iterated function system, yes, yeah.
Sorry to interrupt, Prasanna.
Yes, please. Tell me.
So one thing I was wondering is in this fold operation in general,
right.
It is somehow different from just restricting the domain of the variables, right? So you could also imagine that if I had a finite domain, I'm never going to leave it.
Right. Right. So of course, basically you want, you need, so there's a function, right? You're putting your state at some time, and this function gives you the state at the other time. So you can think of different functions, of course, but you want a function such that it is bounded in a certain interval. The interval can be very big. So I'm not saying. So for instance, I could actually, so if you look at this map, if I took R here I have defined it in the interval 0 to 1. If I don't, it is not going to be restricted in the interval. So this first one, if I take it not in 0 to 1, it will actually have a part which is going to in fact go off to minus infinity. So all these are defined in the interval 0 to 1. And if R was greater than 4, again, I can't keep it bounded in the interval. So you have to plot the function to see that your function is contained in the interval of your choice. So it's not completely, not anything will do. So in fact, one of the good exercises is to just see this map and see how, under what conditions it stays bounded. Okay, so yeah. So as you can see, this horrible, extremely, this comes out of these things, right? You wouldn't have thought if I just put 2x mod 1, I would get something like this. I mean, I haven't done anything complicated. I've just done an iteration of this object.
Sudeshna?
Yes.
Here.
Tell me. Huh? Yes.
I was wondering if this boundedness,
Yes.
can I think of something like a Poincare recurrence for this system?
Yes, of course. Of course, you can think of a Poincare recurrence for the system. In fact, it's one of those really. So, for instance, so of course it's aperiodic, right? So at no point does it come back exactly to itself, because then it would be periodic, right? It's a deterministic system. If with infinite precision it came back to itself, it would repeat. Now, what happens is that though there is a result which says that though it won't come back exactly to itself, it will come back within a neighborhood which is extremely small of itself. So there are these very, almost, very, very attractive demonstrations of the Poincare recurrence, where you take a complicated picture in two iterates. You can't recognize it because it just becomes a very different picture, and maybe in the 100th step it begins to look like itself. I mean, it's one of those things which we like to play around in the career. But yes, of course, yes, that is definitely there. So in fact, maybe when I look at this example, the 2D one, I'll mention the recurrence one more time there. So this is a
Professor
area.
Sudeshna,
Yes.
sorry, just one question. In the
Yeah.
previous slide, you
Oh,
showed
this one. Yeah.
xn plus 1 is 2 times xn mod
Xn
1.
mod 1.
So this binary shift map, I see it to be just a linear map. But
yeah, piecewise linear. It's a piecewise.
Piecewise
So
linear,
you
because
take it exactly, and so is this. This is also piecewise. It's a tent.
right.
So both of these. So that's why I said how simple is it. This one has a quadratic non-linearity. This one has these two are piecewise linear maps. Exactly. So mod 1 is all intervals are 0 to 1. So it is two straight lines with slope 2.
But what happens in the binary shift map, as I see, it goes to the, let's say 0 to 1, and it comes back to 0. Whatever is 1 comes back to 0. It is like a
you take the
periodic
remainder.
window.
You take the so basically that's why there are two straight line segments, right? Of this. If you plot the function, the function 2x mod 1 in the interval 0 to 1, you'll get these two straight line segments. So it's piecewise linear. It's piecewise linear.
Okay, sure.
But that's what, and actually it maps. So if I took a initial condition in a binary decimal, so just a 0 point, because it's between 0 and 1, I can expand it like a binary decimal. This map is just the decimal point going along, just shifting along. That's why it's often called the shift map, because it is like a shift. Okay. Right. Okay.
Thank you.
So, yeah. So so I had this Arnold's cat map one, because it's a very nice thing. I took it from University of Maryland, one of my friends' page. So this again, as you see how small, how easy it is to write down 2x plus yn and xn plus yn. And this is actually, because it's in 2D, one can demonstrate it very nicely. So here is a pixelated map. So it's in a box, 0, 1, 0, 1 box. So 0, 1, 0, 1 box. And this map, just one iterate I'm doing. So the first thing is the stretch. And then the mod 1 cuts up this poor cat. I mean, you have to, of course, feel somewhat sorry for it, because you first stretch it, at least then you can recognize it. It's a stretched cat. And then when you cut it and put it back in the box, see, we also in classical mechanics have boxes. So when you add a cat, so then you put it back into, stuff it back into the box, it looks like this. So in one step, it looks, well, I dare you to think of this as a cat. But to come back to the question on Poincare recurrence, do this hundreds of times, suddenly you'll find a point when it will recur to a fuzzy version of the cat. That's why it's so. So it's a set of very delicious contradictions. So you have determinism on one hand and unpredictability on the other. You never thought you could use these things in the same sentence, but that is the fun of it. Okay, so now I have to get on to my stuff. Okay, so what I wanted to actually share with you is how can one use this knowledge of classical dynamics. So this is some new stuff. You have learned so many new things. So is there, I mean, now time has come maybe to flip the question and, say, what can this sort of new concept do for us? Can you make it work for us? So that is the whole idea of the rest of the talk. Now, one can say these words, harness and exploit and, lovely words. But the main thing one has to do is one has to find a way to use these things in a direct and efficient way. You cannot sell this idea to a engineer unless you're able to do that. And so here I'll indicate two particular two-pronged attack. One is the use of controlled chaos, and the other would be to exploit noise and nonlinearity. So what is this controlled chaos thing? So do remember, I've been saying how things are flying apart. So you would feel that perhaps controlling it would be a very hard task. And it indeed is. You have to be a bit clever. You have to somehow get the dynamics to work for you, okay? Rather than doing a hatchet job where you're suppressing the whole thing. Okay, so that would be an idea. So I would try to use this approach where I can extract a large range of patterns from the dynamics and see how I can use it. That would be the idea. Okay, so let me put the scheme I have. Okay, so this is a method. There are other methods. I'm putting the one which I thought of, since I'm giving the talk. And so this method is something which I called thresholding. Okay, that's simply because, or I could probably call it a dynamic range limiter. Now, it is actually extremely simple. And simple is a good thing here. You want to give a method which is not too complicated, which does not have too many computations in implementation. So this is what I did. If X, one variable, even in a multivariable system, I pick a variable of choice, I monitor it. Anytime this one exceeds a threshold, I pull it back to X star. So the threshold is X star. If it goes above, I pull it back. So it's like a Lakshman Rekha. If it goes out, I just grab it and say, come back. Okay. And so this, if I think of a broad principle underlying this one line thing, which you can put in your program, you can actually even put in the lab very easily in many experimental realizations. The thing would be a dynamical range limiter. So it had a dynamical range. I snipped the range a little. Okay. Now the question is, does this gain us anything? Okay, you've done this. It's so simple. And the action though is drastic. The action is that you can clip the chaos into cycles. And so basically you take this thing, you cut it, you stitch it back together, and you can generate a whole lot of desired stable patterns out of chaos. And why is this chaos even advantageous? I mean, I could have done this with the oscillator. The point is that in chaos, you have all these sequences naturally. So if you can sort of clip them or prune them and in a stable fashion, then I can use all kinds of sequences. Okay, so it has all this stuff which I can exploit. If it didn't have the temporal sequences, of course, I'm working with much less. So that is the idea. So this is a correspondence table for threshold and the controlled period you get out of it. It is for that chaotic logistic map where R is equal to 4 in that example I gave, which is a completely chaotic system, which with the attractor, which covers the full range 0 to 1. It's a full attractor. Now, if I put different thresholds, if I put half, for instance, I get a fixed point. So the whole chaotic system just sits at a fixed point. If I put it in this range, I get a period 2. It bounces between x1, x2 forever. I can get period 4. I can get 6, 7, 9, what have you. I could have gone on through 5 slides with this. But basically, what do I get out of it, which maybe makes an applied person happy? What I get is a lookup table. A lookup table which tells me I have threshold on one side and what I control it to on the other side. So I can just give someone the table and they can directly get whatever they want out of this module at will. Okay, so I can get what I will call a flexible pattern generator. It's quite powerful actually, because these are a very wide set of patterns, okay, which you can get out of that same unit. And technically you can show analytically that the system is actually trapped in what is called a super stable cycle. So from full chaos, you come to something where actually the Lyapunov exponent is minus infinity for a super stable cycle, but that can be shown exactly. And because of this extreme stability, it's also very short transient. So once it comes to the cycle, it's stuck there forever, which is again very good for applied stuff. I didn't think of it that way when I started off, but it was neat to just do the analytical stuff. But actually, when I later on, when I came back and thought about it, it did have all this potential in it. And we also use some properties which I have not mentioned, like ergodicity, which guarantees that at some point you will cross the threshold. So you're guaranteed that you will get trapped in this. Yes.
Just a quick question.
Yes.
Pardon my ignorance.
No, sure.
I am wondering so when we say something is a period 2 or a period 9 solution, what exactly do we mean?
Right.
This is basic chaos, but I don't know this.
No, that's okay. So in fact, it's not chaos. So suppose I took, so that example I showed was for a logistic map. So map discrete time system. So if I have a fixed point, it would mean that after some transient dynamics, my system will sit at one point. So xn plus 1 is exactly equal to xn. So basically, it will keep.
That makes sense.
So period 2 is x1, x2, x1, x2, x1, x2. So x1, f of x1 is x2, and f of x2 is x1.
So it's like a limit cycle of some kind.
Yeah, except that a limit cycle is actually a continuous time system.
Okay, so
this was for discrete time, so I called it period 2. Okay. I will show a limit cycle in a bit. Yeah. So
I am related question little bit. If we try to think in terms of phase space trajectories, means trajectories chaos is not just trajectories may behave in a weird way, but we need to have certain like a topological mixing to really say that system is chaotic or not. Means they can cross each other, but that doesn't mean system is actually chaotic. But
so that is the part which is the part you can exploit. Suppose I had that same very random looking thing with the same probability distribution. I can make a random number generator.
I see.
Right? But that will not help, because I'm also going to use the I'm also going to use the underlying determinism. So it is a mixture of that richness that you're getting, all that thing which is very complex, but it's also the determinism, because at the end it's going like clockwork, behind this. And of course all the properties of ergodicity, all the properties, all of them are preserved. In fact, there are so all of those have to be.
I see. So maybe one more.
Yes.
What will be the definition of Lyapunov exponent if you are putting a cutoff?
So no. So here, the Lyapunov the definition is the same, of course, but here what happens is, so what happens is when you clip something, so you think of your trajectory, say something. Okay, maybe I'll show one picture which might help you visualize it. I don't have it. Oh, I'm sorry. Okay, I thought. So suppose you think of a trajectory. It's like beheading it. It's like or cutting it. So where you cut it, it's flat. So do remember, when it's flat, it means that the slope is 0 at some point, and the f prime is actually one of the terms in this. So, and it's multiplicative. So if one thing goes to 0, the whole thing goes to 0. So that is how you can show actually exactly that it's going to be super.
I see.
It's by construction almost.
I see.
Okay. Yeah. So anyway, so all of that was completely done analytically, and long back, actually in 1993. And actually this one didn't even have it. I had it in a subsequent paper. This one, 1994 paper.
I think I see a raised hand. Maybe if you can ask quickly. And
yes. I can't quite see the hands for some reason. Oh, maybe I'm not looking at the thing. Okay. Yes, please. I can hear you, but
so I have one question. This thresholding, can it be mapped to systems with periodic boundary condition?
boundary conditions, as in you mean oscillator? I mean, you can put it for anything, right? I mean, I mean, in the sense, as a algorithm, you can do it for everything, for anything, right? You can, nothing in the algorithm says that you have to implement it on chaos or chaotic system or a system of a certain kind. The only thing is that you want to get some mileage out of it. So I didn't quite get periodic boundary conditions, but did you mean an oscillator of sorts, or
Yeah, any
yes,
system
of
which
course
has
you
a
can. Yes, yes. I mean, of course you can. You won't. I mean, you won't get that much out of it. That is the whole thing. You get much more out of this. The pattern generator has much more possibilities if you have a chaotic system. That is, so that's the advantage of chaos. Is what. Of course you can do it. Yes. I mean,
okay, okay.
no problem. Of course. In fact, Murali did it, and first thing you check it with that to see if it's okay. Then you try other things. Yeah, yeah. So yeah. So anyway, this was, and actually in this particular PRL, I felt a little. I mean, I was a bit happy that it was featured once in News and Views. But John Maddox had said that this was a model in search of problems. So otherwise he had said nice things, but I felt a little bit, as if I should push it a little, to show that it's useful for something. And so I thought his comment, which was maybe a little bit negative at that time, did push me on later on. And so this is actually a tabletop experiment, can be done in very, very quickly, and done by my collaborator and long-term collaborator, Murali. He knows circuits. So I just have to tell Murali, put this threshold, and he'll just do it. And so here he's got fixed points, 4 cycles, 1, 2, 3, 4, 7 cycle, I think, and 10 cycle. Okay. Now, but people have pushed it beyond this tabletop experiment, and Morai's group, I had just told me, well, not just, already 3 years now, that they have on a chip 120 of these threshold controlled. So it was, I have no idea how they do these things, but he says it's exactly the same results which you can get through analysis, which they have implemented. Well, there were no approximations in the results. So if your theory is right, it should have happened. But it's always nice when it does. Okay. Now, just run through a couple of examples of continuous time systems, because people love differential equations. And so here is, for instance, ODE, which is third order. And this has limit cycles. Somebody asked me about limit cycles. So this was the chaotic attractor. It looks like a band, and this is chaotic. Now, if you think of the threshold, it's like putting a wall, like a wall in phase space in one side. But do remember, there are 3 variables, and you're doing it to just one. So that was our first thing. Can you clip one variable and ensnare the full system? Or do you need to clip all parts of your phase space? And the answer was, we actually could do it with one. So this was one of these limit cycles we got out of it more. And here your period to, because somebody did ask, comes in, right? 1, 2, and 4. This is a double scroll chaotic Chua circuit. People have it in labs, and putting this precision clipping part is very, very small and easy. And this whole butterfly attractor becomes fixed points and limit cycles also.
Sudeshna,
yeah. Yes.
So if I'm sort of doing this in a lab, I am thinking that this is more of a kind of a kicked or driven system, right? It's no longer completely closed if I do this thresholding. Am I right?
These are all dissipative systems anyway.
Okay.
Yeah. So if, in fact, I mean, this was one thing which if you try to do this on a conservative system, that's a different point.
Okay.
Yeah.
Okay.
Yeah. These are
sort of
yeah. Right. Yeah. True. So, and the last somewhat stringent test was a hyperchaotic system. This was a system with more than one positive Lyapunov exponent. So one way of seeing it is that it has more than one unstable eigendirections. So the question was, can I clip one variable here and still rein in the full system. Because, you know, you feel it sort of has these two directions in which, you know, it is running away. Is it enough to, you know, bring it back in one? And I don't know. I mean, I honestly, whichever way the answer would have swung, I would have tried to argue. But the way it's worked was that it controlled beautifully. So this is the hype. And this was, by the way, in experiments. Okay, so, I mean, it was done in theory as well, but it was, these are from experiments. So it seems to be a very potent, very simple algorithm, which gives you a lot. Okay, now I thought after, sorry, I'm losing charge here. So after getting this gadget sort of thing, which gives you all these patterns, the next thing is that can we put it to some use? You know, can we make it work for us to do something, a killer application? Okay, and so it's giving you rich variety of behaviors. It has flexibility because you can do this very, very easily over and over again. And so what we tried was to use this to design flexible hardware. So basically now I want my chaotic system to act as a logic gate. And why would that even be fun? It could be fun if you could make this logic gate reconfigurable or flexible. So somehow if I have a module which can be different logic functionalities at, you know, on demand, that would give me a much more powerful you know, set of gates to work with. So this is what we were trying. So so actually there's a very nice Scientific American, not written by us, by a journalist, but I think he did a good job. And so even if these papers are dense, this Scientific American article is quite nice. Okay, so what we thought was, as I said, we wanted a dynamic architecture. And the aim is, or the hope is, aim is a strong word, actually I should have put hope, is to implement all basic logic gates with an ability to switch between these. Okay, so if we could do it, it would serve as a general purpose device, which would be more flexible than statically wired hardware, because you can change your functionality. Because otherwise what happens is, you know, you sit, your machines are made from a family of NAND gates or a family of NOR gates. But here everything could actually change its functionality, and that would be a fun thing. So here is an illustrative example. Again, I thought I would just do it with the with a map, because it's easy to just see it. Now, let's take the simplest idea. Say the state of an element is X. I give it inputs, I1, I2, something. It raises its state to that plus I1, I2. And the threshold mechanism just tells me that if after an update, it becomes more than threshold, it gives me output 1, otherwise it gives me output 0. Now, if I want this to work as logic gates, I will have to satisfy this truth table. Okay, so here I've put some of the basic logic gates, AND, NAND, OR, NOR, XOR, NOT, etc. So if I put these I1, I2, my system should respond in a way such that the output should always be 1 or 0, depending on this truth table. Now, how do I see that it can do that? I can do that simply by seeking solutions. So this table is the set of equations I must satisfy. These are the necessary and sufficient conditions in order to implement those logic gates by that chaotic map. So in order for the same chaotic module system to serve as any of these, by simply changing this threshold, I will have to satisfy these. Okay, this equations. So don't have to stare at them, but you have to sort of believe me that this is reflected in this. Now, this is the one point to take home in this. Robust solutions to those set of equations exist only if the system is sufficiently nonlinear. And in fact, for the map, all the various maps we tried it on, it existed only when it was chaotic, because at the level of nonlinearity we had, the system was chaotic. That was incidental. You don't need it in the solutions, but sufficient nonlinearity is necessary, and that often entails chaos. Okay. And the other way around is probably true, that if you have a chaotic system, you have a very good chance of getting all these solutions. And so, one word summary, the nonlinear dynamics enjoys both the richness and the determinism, so that you can work backwards and design. Okay, because you can actually solve the equations, you can get the inverse solutions, and design the gate. Okay, so some of this, of course, are very IEEE type journals, because we had a computer scientist on board, and there's a whole bunch of patents. And this is an experiment which just says that this system, by changing this parameter, could behave as a NOR, and then if I change the parameter, behaved as a NAND. So it was a morphing logic gate. It could behave differently depending on a control signal that I gave it. Okay, that was the whole thing. And it could do that because it had that richness of behavior. Okay. You could also use many different iterates. So this is a colorful picture, which once made it to a cover of something, that if I take different iterates, I can try to get that truth table, which I was trying to solve, but different iterates will give me different solutions. And here is actually the full spectrum of logic gates, starting from dead, where everything is 0 or everything is live 1, and everything in between. And so basically, it's a very rich system. Either you use the initial conditions or the threshold, or you use the number of steps you take where you tap the output. That's also done. So obviously, once you get to iterations beyond 5, I think it's not very feasible in applications. But up to 4, 5, I think they had no problems getting it done. Okay, and some of it has gone beyond my reach, and so there's a company called Chaologics, which I think has just got acquired for undisclosed sum by some other company, which is developing the VLSI implementation of this. And they have a first generation, which is not too bad. And, so sometimes we get featured in all these journals, or magazines, which you never even read, like MIT Technology Review. But if someone says you figured there, you go and look at that particular one. But the fun thing is that it actually came from trying to understand maps and ODEs. That was, I thought, for me, the fun thread. Okay, so can I have 10 minutes, or because there were some questions, or
Sure. Huh?
Yeah. 10 minutes is okay? Yes. Okay. So I'm actually terribly behind time, but I just thought I should mention this one. And let's see how fast I can do it. I think 10-15 minutes, I will definitely stop wherever I reach. Okay, so I had sort of put in the abstract that I'd also indicate how noise, all this thing before was completely deterministic, no stochastic influences, but noise is everywhere. So various people had, asked us at various points, how do we deal with noise and stuff like that? And we were trying to, thinking about it, but didn't have much of an idea. So then we thought, let's go back to the drawing board and see what are the situations in which noise and nonlinearity have actually cooperated and given better or enhanced operation. Okay, because in some sense, whatever you do, your computational platforms are continuing to shrink. You are going to encounter fundamental noise. You cannot suppress it. You can't eliminate it. You can't wish it away. You might as well live with it and work with it. Okay. So is there some strategy here that one could fall back on? So one of the things which we went back to was stochastic resonance. Okay, where there are many examples, but let me just put it in a sort of one line to sell it. That is, when you add an appropriate amount of noise, the noise can often boost what you think of as a signal. Okay, and there are cases where you can help detect the signal. Actually, engineers used to call it dither and were using it without using the word stochastic resonance. And so essentially in your signal to noise ratio, it is actually maximized in the presence of non-zero noise. Okay, so that was the surprise, that the noise, so this was sort of counterintuitive. Instead of making things worse, there is a window of noise where things get better before it gets worse, of course. Okay. So this was, then everybody took it up and it was there everywhere and people were trying to explain ice ages with it and stuff, okay? But engineers had been using it way before this, by the way. So they would say, oh, of course, we've been doing this, okay, I mean, you have discovered it now. But for physicists, because we tried to, understand it through escape rates over barriers and all, it was a different game. Okay, now what are we trying to do here? So we are trying to exploit nonlinearity in the presence of a noise floor to get more reliable logic operations, if possible. Okay, and we think, of course, that this is important because obviously in the design of any device, you will need to take, need to confront noise. And what we showed, the bottom line up front, because I may not be able to reach it, is that in an optimal band of noise, we showed that the system, nonlinear system, actually gave an output which was the most consistent logical output of these input signals. Okay, so I have, and we called it logical stochastic resonance. I thought it was a bad name, but it was there and now it's stuck and I see people are using it all over the place. Okay, so I'll do it with a simple example because, no point, just so that you get, see it in one example. Many complicated examples are there. So if you take, say, a simple system, nonlinear, because it needs to have wells with two potential wells, say, to begin with. You add an additive noise. It could actually, well, here I've added additive zero mean. You could have colored noise, you could have multiplicative noise, but some noise. And you have an input. Because of course you're thinking logic gates, has to have input, has to have output, and the correspondence. So the input is low amplitude, because if you give a huge amplitude, okay, the system reacts because it just sees this big, you give it a low amplitude, sub-threshold, and see whether it gives a big output, because that is the engineer's dream, low amplitude input and huge response. So suppose you have two inputs again, I1, I2, binary logic, and then so basically these will add up since I1, I2 are symmetric, so you will have three steps, 0, 0, 1, 0, 0, 1, and 1, 1. And now I feed it. Okay, so say I take a cubic nonlinearity, two wells, bistable. Now I add this thing. So one is at roughly at -1, one is at +1. And I call one of these output 1, other one output 0. Very simple. And so what we get is, you give these input bits, there is some noise, there's the nonlinear system, and this is going to jump from well to well, and you want it to jump exactly as the truth table dictates it. Okay, so noisy nonlinear system forced by this input is yielding a logic output. And here is a experimental one, and I'll just, maybe this one you can carry back with you. So here is so the one bottommost one is a lot of noise. So obviously it's just, this is not giving you anything. It's just jumping at will whenever it wants because the noise is so high. So there are two wells, it's just, jumping back and forth. And this is no good as an output. No one is going to look at this and say, I can work with this. But look at the one with low noise. This noise here is too low. Why? Because sometimes the system is stuck in a well and can't make the jump in response to the input. So sometimes this is stuck here, whereas at the same thing, this is stuck on top. So it's inconsistent, it's unreliable output. In this sweet spot in between, which is quite a wide range of moderate noise, it jumps exactly according to the truth table, and also its transience is very low. So it responds fast, and it kind of always exactly as we wanted it from the truth table. It took a little bit of designing backwards to get the right potential. That's part of, the job. But once you do it, you can get this consistently. Okay. Sorry. Yeah. So basically, this robust operation is only in an optimal window of noise. Okay, you can't do with no noise, and given a noise, you can always find this nice window. Okay, and this, of course, was lots and lots of experiments have been done since then, including some from our group and from many other groups, and it's actually very robust. Okay, you could also add a little asymmetrizing bias. So you can add a constant. Now, if I add a constant, very easy to do in the lab. I just add a constant, but it has this effect of rocking the potential slightly. And by doing that, again, I go back to my old idea that I can morph between outputs by just using this bias. So I'm trying to, combine the ideas of flexibility there along with noise and this sort of logical stochastic resonance. So what one gets is these bright spots are the nice spots of operation. The probability of getting a correct answer is 1. So it's very, very reliable. And this is the noise on the x-axis. Y is my that constant bias. So as I change the bias, I can get 2 different logic, NAND on this side, NOR on the other side. And as you can see, the spot is somewhere in between. There's a moderate amount of noise where it works perfectly. People have done many experiments. I'll just show one. This was done in Mohanty's group in Boston. He had nanomechanical oscillators. So one day he just said that I have these oscillators which exist in 2 vibrational states. I said, wow, now just add noise to it and inputs, and let's see if it becomes a gate. And so we managed to do this noise-assisted nanomechanical logic gate, which was done in his lab. I'm a theorist. I actually can't do any of this, but people seem to take it up and do it. And this was, it was quite small and very power efficient. And these are from the experimental data. Okay, it gave and or depending on this constant bias. And as you can see, when it's low noise, it gets stuck once in a while in the wrong output and can't come out. When it's too high noise, it does this black gitch pitch, which is no good. And the middle spot is very, very very reliable. Okay, so I will actually not, I think now I am at 5 o'clock, so I will not go over all this. There are many examples which are done with different systems. So I think what I will do is I'll just go to my last slide, because I really dislike people taking more time, so I shouldn't do it myself. So let me go to a summarizing slide and skip all this, okay? So just one thing. So there are a couple of nice articles written on this, nicer than, how, one can't do this popular science thing as well as the journalists can. Both of these are pretty good. I think the focus one is better though. Okay. There are lots of other groups which are doing a lot of experiments on it. And some of the experiments I don't even understand, but I do know that they are corroborating the general idea. So let me keep it at the last slide. And sorry, none of these are there. So I'll just keep it at the last slide. Okay. So, and I'll take questions. Okay. Okay. So maybe I'll just say one word and take questions. So what I have tried to do is to show that one can exploit chaos for the design of computing devices. But so rather than suppress chaos, we try to use the opportunities offered by chaos, which is the richness in all the temporal patterns and the determinism, which allows us designing. And I also tried to show very briefly that one could connect noise and nonlinearity, again, gainfully, and make noise also work for you. So you first try to get chaos to work for you, and then you can also get noise to work for you. Okay, so I'm done.
So thanks very much for the wonderful talk. And so if anyone have any questions, you can ask now.
I saw some things on chat. Oh, okay. I saw some things on chat.
Yes.
Points. I think somebody said that imposing boundary conditions was same as thresholding. Oh, okay, okay. Well, not necessarily, because there, see, after all, in thresholding, the system just does its, you actually let it do its thing. You only touch it when it's at that point in phase space where it has exceeded. So you have to do very little to get a huge effect. Okay, but in some sense it is true. If you want to calculate backwards, you will say you are looking for a solution such that if if x is greater than x star, at the next nth iterate, you will again exceed x star. That's how I did the calculation. Actually, you can work it out completely. Yeah.
I have a
Hello.
question. Hello.
Yes, yes.
Say this. Could you say about the initial conditions of the chaos and the boundary condition, how it would determine the evolution?
Huh. So of course, I mean, it is of course, as right in the start I said, it's extremely sensitive to initial conditions. But the thing is that so if I just have a chaotic system and I see its trajectory in a very short amount of time, if I took a nearby initial condition, it would be a very different trajectory, right? Except what happens is that we have attractors. So which would mean that there's a set of points in phase space where, for a dissipative system, where your trajectory would come and then it would sit on that set of points. So in that sense, it's very sensitive. The exact trajectory is very sensitive, but the attractor is very robust. So as I said, it's always full of these very contradictory ideas. And for the control thing, it doesn't matter. It really doesn't matter, because the moment x is greater than x star, it's caught. And so that's the nice part. So there it doesn't matter. So because in the lab, in all those experiments, we can't even set the initial conditions. We don't know where it started. I mean, you start your machine. I mean, we don't know. We don't know where the initial condition is.
So the related question: is it possible to identify attractors from the beginning, or it is?
Yeah. So you have to. Technically, you have to, it can have a period of transience or transients, and the attractor is the long-term behavior of the system.
Yeah.
So often, so for instance, you might have to wait for a little bit. So in numerical but it's often a very short transience, but you have to wait for it to get attracted to that limiting set. Yeah, you have to. So sometimes, in experiments, it's so fast that you don't even, you can't even see the transient time. In numerics, often you have to wait for maybe of the order of a couple of cycles to
Okay.
reach it. Yeah.
Okay.
Yeah.
I think there are two raised hand actually. So
Yes.
yes, please go ahead and ask.
Yeah,
Gurudat?
yeah. So Gurdat here. Yeah.
Yeah.
So
Yes.
I,
Hello.
I was trying to understand this chaotic
Sorry, I lost your voice at some point.
Hello?
Hello, I can't hear Gurudat actually, if he's
noise.
speaking. Yeah.
Yeah, because resonance is something that, so I'm imagining is something that frequency or a time pattern in the signal and the noise are matching,
Right.
something
Yes.
like.
Yes.
But the role of magnitude,
Yeah.
because yeah, so that
Yes.
is not clear to me. And SNR
Yeah.
is still greater than one, should be
Yeah.
greater than one, or
Right. Yeah. So absolutely right. In the original thing, when stochastic resonance came, all these nonlinear systems were driven by a periodic signal, and these were sub-threshold. I mean, in amplitude. So you would have a very low amplitude periodic signal. So their thing was that can you detect this very weak signal through this system? So from the engineers, but in fact had that very much, because they had this signal detection thing, and they were, you know, they have these very weak signals which they want to detect. And even otherwise, from the physics point of view, you want to see if you were driving a nonlinear system with a periodic thing, which is why, as you rightly said, the word resonance does indeed have a frequency. You know, you imagine a frequency, which it was in all earlier studies. It was like that. Of course, we don't have a periodic thing. It's an aperiodic train, which is given by the outside world, the user. So, which is why, though it is inspired by, it is not exactly stochastic resonance. Yeah, but in stochastic, it's subthreshold, low amplitude, periodic drive. And the SNR is of the system hopping from well to well with the same frequency as the drive. So when does that hopping synchronize with the drive frequency? Sort of. Yeah. I don't know if
Srijit,
I see a lot of hands. Yeah.
3 more actually.
Oh.
Please go ahead.
Yes, I see
Srijit,
hands, but I can't hear anything.
No, they are all muted actually.
Oh.
Asking them actually directly to ask. Srijit, can you ask?
Yeah, thanks. First of all, a wonderful talk. Thanks.
Thank you.
So my question is also related to stochastic resonance.
Okay.
I mean, the first question is that these systems where this stochastic resonance actually happen, the noise, etc., they are inherently in the system, and in some cases probably some noise has been fed, and this phenomena occurs. Right. So is there any, I mean any part in the study of stochastic resonance where you can tune your noise, which is in your hand, and you get a very good output?
Yes. Yeah, I very good question in some sense. So there are apparently, so indeed, of course, if you want to do a proof of principle experiment, you would like to tune the noise because you want to check what is happening. So that of course can be done. That is not very easy to do. And there, of course, you're tuning noise because you're studying the system. But actually people add a little noise to some of, like, you know, I think one of my engineer friends was calling it a dither noise or something, which they used to routinely do to help signal detection and things like that. So people had sort of observed it, though not quite seen it in that sense. But
yeah, why I'm saying that in medical applications, some of these motor neuron, etc., where I mean people's visual and hearing aids.
Yes, the recognition of or image segmentation or image recognition. Definitely, there are lots of them where you a little noise helps. It's a little bit in the same kind of train of thought. Yes. Yeah. Right. I mean, the other way could be to say that if there was ambient noise, you find out the best operational zone for it, because for every noise, so either the noise is in your hand or the system is in your hand. Yeah. But yes, I have seen people add a noise to help in. Somebody was telling me they had some detection thing for underwater, because I'd given this talk and the engineers were saying, okay, we do something like this, but, you know, we don't call it. You know,
I mean, so the related question was that so sometimes we get these noise-induced transitions, right?
Oh yes. Yeah.
So I don't know. I mean, whether there is a chance of people getting their vision back.
Oh, oh boy, I have no idea. So I mean, the biology is scary for me because I mean, they're just so many things which, it's like take a spherical egg kind of thing, which may not work. But engineering, actually, I feel comfortable with because you tell them to make something, they make it and it works.
Yeah,
So,
yeah.
so I would not like to venture a guess for that. Uh, but there is, yeah, one should
Yeah,
probably.
I mean, the first time, because from the physicist point of view, I think some Italian discovered this, right? That
Yeah.
appearance of ice age in a periodic.
Yes. That's what I'm saying. So people use it. I think I probably even put it in the slide from the Ice Age, and I mean lots of things. I mean, see, once you get this idea that you can, have this cooperative effect of noise, and since noise is everywhere, people tried to see, because see, some things are so weak as signals that you really wonder how it could have such a big effect. That was how the dynamic systems were, people were wondering, so then they suddenly thought, okay, maybe the noise has helped it, because otherwise, if you just looked at it as signal, it shouldn't have responded at all. So
Right,
people
right.
were then trying many things. Yeah.
The last question is that how much one can reduce the non-linearity of a system to see this? I mean, is there any way we can come closer to a linear system and still we can have stochastic resonance?
Well, you need wells. You will have, I mean, no linear function will give you that.
Right.
So that is,
So far, there is no such.
yeah. I mean, you could try to, you know, so this constant bias thing actually was a way of making it more and more linear in some way. So you could try a few things, but no, I mean, I would say it's a very crucial ingredient, very crucial. Yeah.
Okay, okay, thanks.
Okay, I think two more actually. Another.
Hi. First of all,
Hi,
thank you
hi.
very much for the talk. It was super lucid and
Okay.
fascinating.
Thanks.
So I had two things in mind. One is, would it be possible to mail the slides? Because I missed out on some of the
Oh,
rather interesting references.
yeah. And also, I think I probably had 10 slides which I didn't show. I would
Yeah.
definitely, should I send it to Arpon then? Or how does
Yes,
this
yes,
work?
yes,
Huh?
yes.
Okay, I'll send it to him. Yeah. There'll probably be some extra stuff there, which,
Yeah, sure.
which
Thank you
I
so
didn't.
much. And the other thing is, could you quickly go?
Sorry, I missed
I
something.
just said drop it in, but
Okay. Okay. I'll do that. Huh. Yes.
Right.
But you had a
And the second
question.
thing was, yeah, I'm just a beginner in this. So could you quickly go through the idea of Arnold cat map once again? That
Oh,
seems
okay.
very interesting.
Oh, okay. Yeah. So basically, this is one of the. So as I said, that the simplest, that in some sense, the simplest system which shows chaos is a 1D non-invertible map, and the simplest invertible map, so that is which has a unique pre-image, is it has to be 2D. This comes from Poincaré, Benedictson, etc. So the simplest 2D invertible map. Sorry, I'm doing this not very properly. Okay, I have overshot. I thought I should. Yes, this one, right? Yeah. So this is a very classic example of one of the simplest invertible maps. Okay. So by invertible, I mean that, if you write an inverse, it's a well-defined inverse of this map exists. Okay. So these were non-invertible because if you see it, that for every x of n, you can have two values of x which can lead to it. Because suppose you have a non-linearity, two values can give the same x. So this is
Right.
in fact so you can think of this as one of the simplest area preserving. It's also area preserving, this mapping. If you look at the determinant, you will find out. So it's area preserving, two-dimensional system. And actually there are Hamiltonian systems which this mimics. So lots of people try kicked rotors and things, which with some massaging, a similar-ish thing. So as you can see again, some of the thing comes, otherwise it's just a stretch, right? One is become 2x and just pulling it out. But it is the mod operation which is really messing it up. because you see, just
Right.
the stretch would have been a distorted cat. You can live with that. But it's this mod operation, which now in two directions, of course, because it's in a box 0, 1. It's and that this operation is what is really giving something which is like in one iterate, which looks so simple, has given you an image which is unrecognizable, which is why lots of people used to get very excited thinking maybe we'll have a cryptography or a secure communication application. Because you see, it's so, it manages to scramble it so much that, you know, you can't actually, unless you knew the map, you can't work backwards and know what your X and Y were. Yeah. I
Okay,
don't
thank
know
you so
if,
much.
okay.
Yeah, Prashant.
Yeah. So thanks, Sudeshna. It was
Yeah,
a great talk. Like I echo everything that people said. So
Right.
I couldn't help notice this thing about making logic gates with these chaotic systems. So one thing that you mentioned makes sense easily, which is that you have this flexibility. So you can make the system do all kinds of gates. But I also saw somewhere in the slides that it's talked about very fast gates. So I'm just wondering, something
Yeah.
intrinsic to the way we design with this chaotic systems that it makes it fast, or where does this
Yeah. Right. I don't know if I wrote fast. If I did, it wasn't.
maybe it was this one of these
Okay, maybe the ones where those guys had
aha,
designed it. Ha. Right. So
right.
how they make it? Yeah. Uh, so okay, first up, I had no role to play in the fastness of the dynamics, because, you know, the dynamics is what it is. But
Right.
they have managed to implement it with very fast electronic circuits, actually. I mean, very fast systems. So the basic thing is that, you know, there are lots of control methods. A very large number of them are what are feedback methods. So basically, you see it, you calculate something minus target value, and then you give some, you know, you do cut with a parameter or with the state. Now this is actually very slow, because you have to do a computation. You have to do, now the way we are saying it, it's a very, the method is very fast, because you have to, you know, you don't have to do a calculation while implementing it. So a lot of the control methods of chaos have that problem, that people had to invest a lot of, you know, just to control it. There was so much effort that then, you know, it's not so useful, because, you know, if you are investing so much time and effort to do that, then the use of it has to, there should be a trade-off, right? There's no such thing as a free lunch. You can't just, you know, get flexibility and so you would like to minimize that. So I think maybe I did that, but I don't know if
Okay.
it's
As
it's
just
as fast as it, yeah, they managed to do. Yeah.
so somewhat of a follow-up, I think, to an earlier question. So this nanomechanical resonator is really
Right.
and the example that you showed, where in your calculations before that in that system, so there you are sweeping, is it the sort of the it's literally the strength of the noise, right? So it's amplitude of,
Right.
not
It's, yeah.
band, in the sense of a, what is the frequency band where
No, yeah. So here we were just actually in that example I showed, I was just sweeping the magnitude. I mean, you know, just you know, so took some zero mean, you know, variance one noise, and stuck a number in front, and, you know, did it. But lots of people have done lots of work after, you know, it's, you know, and they have people have done colored noise, people have done multiplicative noise, some we have done, other people have done much more than us now after that. So all kinds of scenarios have been used. People have done a mix of periodic signals plus noise, you know.
and
But then those are all, I thought, you know, just getting it better, but the idea is not that different, I suppose.
and these are, again, at the end of the day, these especially because I saw this nanomechanical oscillator,
Yeah.
it become a sort of a base idea for a sensor of some kind eventually.
Yeah. That
hope, or
that is the hope. Yeah, I mean, so we're trying to get Mohanty to push the sensor idea. It was actually so easy to do the gates, but for sensor, he says, I don't know whether it should have been very easy though. I don't know. We still haven't got it done, but I would think it would be a nice thing to have a little oscillator which would be a sensitive detector of sorts. Yeah, thank you.